Hello, we are Group 7 and our project is the Drop Tower Impact Test. I'm Jonathan, and with me are Michael, Logan, and Jace. We also worked with Allie, Ryan, and Owen. We were requested to build an apparatus that could produce acceleration, velocity, displacement, and force data of an impact. The apparatus had to maximize data points during each impact of each test. As well, it also had to provide consistency between trials by matching peak magnitudes, all while having the least amount of noise possible within each trial. Finally, the apparatus must be simple for novice users to consistently achieve good results. Next, we made a house of quality and determined the functions and constraints of our apparatus. We also determined 3 interest groups: the consumer, the manufacturer, and the marketer. The customer would be most interested in the function and design of the apparatus. The manufacturer would be interested in the safety and cost of the design. And finally, the marketer would be most interested in the cost and design as well as safety. Next was our design process. We had 3 ideas for our design, and they consisted of the spring launcher, the swing arm, and the drop tower. The spring launcher has the phone attached to a spring, which is pulled back and released, causing the phone to make an impact with the wall. The swing arm has the phone attached to an arm, and when released from a height, the arm angularly accelerates into a wall for impact. The drop tower has the phone attached to a collar and fixed in place with a pin. Once released, the phone falls due to gravity and makes an impact with the ground. We decided to choose the drop tower over the spring launcher and swing arm because of its safety, reliability, consistency, and its ease of use compared to the other options. The spring launcher was very unsafe and inconsistent and would not provide good results. The swing arm was much harder to build, much more expensive, and would have been more complicated for novice users. Ultimately, we decided that the drop tower would be the best and most fruitful design.
Here we have the initial and final designs for the collar. Initially, we planned the collar to be a one-piece part that included the phone holder, ball bearings, and collar itself. This initial design quickly became unsuitable for us since unfortunately 3D printing a piece this large and complex would have been very difficult, so instead we redesigned the collar to be assembled from 4 quarter circles and for the phone holders to also be separate pieces. These pieces were joined together by pins on each side and being inserted into slots on another piece sequentially until all 4 were put together. Here we have the initial and final designs of the collar modeled onto the tower. On the left is the old design for the collar, and on the right is the new design. In the middle is a video demonstrating the collar in action. Here you can see the collar slide down the pole when the pin is removed, and which creates a measurable impact on the base. This video is a demonstration of the process of assembling the collar out of the 4 pieces. Clearly you can see how it's as simple as aligning the pins of 1 quarter to the slots in another, and the 2 are held together neatly by the frictional force. The ball bearings should be put on before connecting the pieces. They are also held tightly on the slot part of the other joint. Lastly, here's the dimension drawing for our collar showing specific lengths, diameters, and angles. Also pictured is a 3D model of the phone holder and a real picture of the assembly. One modification we made at the end was to put a hole in the side of the phone holder, glue a nut on the inside, and have a bolt screw into the phone holder in order to hold the phone tight so that it doesn't fly out during experimentation. Now we move on to the building process. Here are some pictures of us during several parts of the building process. On the left is a few of us drilling holes into the pipe. We drilled the holes, starting 9 inches from the bottom and every 3 inches after that, so that the operator has many different heights they can run the experiment from. Next is some rubber feet we put on the base to keep it from sliding, another modification we realized we would have to make later. On the very right is some of us putting the first iteration of the foam impact dampeners on the base, which would need to be removed and modified later. Here are some pictures of the building process of the collar. On the left is the phone in the phone holder part, secured with the bolt and with some cardboard wedges to add some pressure to hold it in place. Next to that is Ryan putting together the collar, holding a piece. In the middle is 2 pieces of the collar after being printed. Printing 2 at a time was a safe enough amount where if an accident happened, we wouldn't be too far set back. Lastly is a quarter of the collar with the ball bearings on the slot side. This piece is ready to be joined with the other pieces. One more picture of the collar with every part joined together. You'll notice some new sponge on the bottom. This is a result of us having challenges with our original catcher, which will be discussed later. Lastly, here's our final design assembly hole. This final design sufficiently met our objectives, and with the data recovered from our trials, we were able to demonstrate consistency, repeatability, minimal noise, and many points of data observable at impact. Here is our bill of materials. As a note, we want to mention how we used some materials that we were able to find available for free from the machine shop, which included the pipe and the plywood. We included estimate prices for them anyway for an accurate bill of materials.
We were asked to create graphs of acceleration, force, velocity, and displacement of an impact event using data collected on our phones while running Firefox. Because of our apparatus design, the phone was following primarily only in the y-axis of Firefox, so the only data we needed to concern ourselves with was the y acceleration data we were collecting. So from this acceleration data, we used Newton's second law of motion, F equals ma, to derive our force data. Here, we interpreted the request as wanting the force acting just on the phone and not on the whole collar. So we used the mass of our test phone, which was 244 grams here, and then we just multiplied that constant by the acceleration data to get force as a function of time. Driving velocity was a little bit more involved. We rounded the acceleration to 2 decimal places. This was a noise reduction method, and we will discuss that shortly. But the method we used to integrate the acceleration data to get acceleration was a trapezoidal Riemann sum, which you can see the formula depicted at the bottom here and a graph representing what this is trying to accomplish. And it makes a trapezoidal area under the curve, which we add up incrementally with time to produce velocity data with time. And similarly, to get displacement, we did a similar trapezoidal Riemann sum integration technique, only this time we did it over the velocity data, and that integration of velocity gave us displacement. And so here you can see our graphs for the requested data. Of particular note is the 6 to 7 data points we are collecting at the time at the initial spike for the impact. This is the maximum amount of data points we were able to get at the time of impact, and our iterations to produce that many and retain consistency will be detailed shortly. Secondly, of great note is our displacement graph. So we set the 0 level as the initial height of the collar in the tower, and then you will notice a final displacement of negative 0.6 meters. This is perfectly in line with the 2 feet of travel that the phone experiences as it falls from this pin height. You can also see a parabolic look to the data, which is what is expected from a constant acceleration fall, which in this case gravity being that constant acceleration. Additionally, in our velocity graph, the phone starts at rest, bounces upward a few times, and the most notable feature of our velocity graph, and that proved our data production methods to be successful, is that the velocity starts at 0 because it's at rest, and it ends at 0, as well as having those spikes into the positive velocity, which correspond to the rebound of impact, which again would, instead of having the collar falling down, would depict a movement upward. Next, to match our peak magnitudes, we were primarily focused in the design on having the phone fall from a consistent set of initial conditions. This is why we have pre-drilled holes at set heights and added a pin dropping mechanism. These ensure that the collar and therefore the phone, have the same displacement each run, as well as having the phone consistently start from rest before each run. Additionally, we use a durable foam that retains its properties between drops. This prevents degradation of our design and ensures that we have the same impact conditions each time. Additionally, noise is unpredictability in the dataset. So all the measures we take to reduce noise, discussed shortly, will also help to ensure consistent results in matching peak magnitudes. And so here you can see that we ran 10 tests of our final apparatus. And then from the data we had from these tests, we found 3 independent peak magnitudes that we could examine. On the left graph shows the peak acceleration data from each of our runs, and the orange line on each of these graphs is the average value. And so what we managed to have is a final standard deviation of only 7 meters per second squared throughout these tests, which means that we can predict that the peak magnitude of experimental runs will be within 7 meters per second squared of our average peak acceleration of 150. We feel that this is as predictable as we can get using Firefox because of the unpredictabilities present in just using a phone to record acceleration and Firefox in general. The middle graph represents the peak magnitude of the velocity right before impact, and the right graph is the max upward velocity during the initial rebound, both of which, as you note, are extremely accurate, and the standard deviations are very small, meaning that we can accurately predict what the values will be each time. So to reduce noise in our data, we wanted to ensure that the data we record is purely from the falling motion, and then any subsequent rebounds that occur from the impact. We did not want any noise in our data that would result from friction as the phone was falling down the collar, so we built into our collar 2 layers of ball bearings evenly spaced around the collar. These were spaced such that should the collar try to rotate and drag against the central tower, the bearings would be the only point of contact between the collar and the tower, so that any friction would be resolved into purely rotational motion. To aid the bearings, we also went with a counterbalance to alleviate most of the rotational moments that would arise in the falling action that could come from an unbalanced collar. And finally, to reduce any noise that would arise from the phone shaking or bouncing as it descended the tower. We use cardboard wedges and a bolt on the side of our phone holder. These act to add pressure and secure the phone in place so it doesn't move. The tower itself also helps to reduce noise by reducing any shaking that could occur, and rubber feet were also added to the base, which prevent any slipping that might occur with the actual apparatus. Outside of our design, phones and Firefox inherently have noise present. To mitigate the effect, we round acceleration data to only 2 data points. Firefox records 9 significant figures. However, it is unlikely that our phones are accurate to anything past 1 or 2 decimal places, so we opted to round it down to just 2. However, when the phone is at rest, there is still noise present in Firefox, but you can note that if you look right above the yellow highlighted line, we are depicting a fall of 4 centimeters. Now, at this time, the phone has not been released from the mechanism and is at rest, and this is just from pure noise. So one method we did to reduce the effect that this would have is we zero out the velocity and displacement right before the fall starts, which is the green highlighted region.
We were tasked to maximize the amount of data points our apparatus collects. We have done this primarily through 2 ways. First, we are utilizing Firefox at its maximum frequency of 100 data points per second. Next, we aim to slow down the moment of impact. This was done by using 2 layers of foam, 1 layer attached to the bottom of the collar, and 1 at the base of the tower, that help absorb the impact. This 2-layer setup deformed about 3 inches after letting the collar fall. We also ensured that the impact only had a small surface area, which helped absorb more of the impact and have less rebound. Before we landed on this design, we went through 2 other iterations. For design 1, we used 3 foam blocks and surrounded them on the base. However, it was too stiff to effectively absorb the impact, so we only had 3 to 4 data points at impact. For design 2, we attached foam wedges to the bottom of the base, as well as small foam blocks on the bottom of the collar. This did increase the amount of data points to 7.4 on average. However, due to wear on the foam wedges, our standard deviation was much larger than accepted at 26.05, making our data too inconsistent. For design 3, we ended on a double layer of foam, 2 small pieces on the phone holder and 2 blocks at the base. We also minimized the surface area at the impact location so that the foam could absorb more of the impact. This had an increase in the data points from design 1 with 6.2, as well as a lower standard deviation of 6.96 compared to design 2. These are our acceleration graphs. As you can see, iteration 1 had less data points than the large spike compared to 2 and 3. Iteration 2 shows more points in 3, but due to the wear on the foam strips, the later graphs start to deviate heavily, making them inconsistent. Iteration 3, our final design, has more data points than 1, and the later graphs were much more consistent. For our velocity graphs, they also follow the same trend as the acceleration ones, where iteration 1 has less data points. Iteration 2 had the most, but couldn't be used due to wear on the foam. Iteration 3 had more points than 1 and much more consistent. Lastly, for ease of use, our apparatus follows very simple and straightforward steps. First, you secure the phone that will be recording data into the holder, then tighten the bolt on the side of the holder and add cardboard strips to keep the phone stable. Next, you place another phone or object of similar weight into the opposite phone holder to act as a counterweight. Then you bring the collar to a desired height and lock it in using the wooden dowel. Lastly, you hit the Run Experiment button on Firefox and quickly pull out the pin to begin data collection. Generally, these steps can be performed in any order as long as hitting the Run Experiment button and pulling the pin are the last step. Here, we have 2 novice users that were operating our apparatus. Test 1 took 19.14 seconds, and Test 2 took 23.62 seconds, and both tests show that it takes a person less than 30 seconds to learn how to perform their experiment without any prior training.
So first what you do is you raise the collar up to your desired height and place the pin through the collar into one of the pre-drilled holes that you desire. Next, we're going to take the backup phone that's going to act as our counterweight and place it in the counterweight phone holder. And little pieces of cardboard just to keep that secure. And then the phone actually running the experiment goes in here. And first things we do is we have a little cardboard just to prevent scratches. And we secure it in place with the bolt. And then we use a couple more of our cardboard wedges to go in place. And now that the phone's secure, you can see Firefox is already open. So what we do is we hit play, and then all we need to do is pull the pin, and that's the experiment. Then you stop, and that's it.